Hello and welcome to the Introduction to Graph Analytics with Python course. What are the topics that we are going to cover? You are going to learn about graphs and graph databases. You are going to see graph analytics in action. You are going to find out what graph analytics tools are out there. You are going to learn about one of the most popular Python graph analytics tool called NetworkX. You are going to learn more about graph databases and especially about Memgraph. And then you are going to learn how to use best of both worlds, Memgraph and NetworkX. Hopefully you'll enjoy this course. Let's start. Okay, so first I'm going to talk a bit about graphs and graph database in general. So what are graphs? Graphs are a way to formally represent a network or a collection of interconnected objects. And in computer science, graphs are common data structures consisting of a finite set of nodes or vertices or points and a set of relationships that is edges or links that are connecting them. Graph database, on the other hand, is a database that uses graph structures for semantic queries with nodes, relationship, and properties. These properties are associated values belonging to nodes or relationships, and they are also called attributes. And these nodes, relationships, and properties are representing and storing are used to represent and store data. A popular model to store this data in a graph database is called label property graph model. So let me first explain you what this model consists of. So as mentioned, we have nodes. Nodes are these little circles which have something inside written. So in this example, we have a person and we have city and location. These are called labels. So each node is labeled with one or more nodes. So for example, person is a node with one label and the city location is a node with two labels. These nodes are connected with relationships. As you can see, these relationships are of certain type. This type is, let's say, married to or lives in. Each of these relationships and nodes have a different set of properties, that is key value pairs. So in this example, a person has a name and date of birth properties, while a relationship of type married to has wedding date properties. So this is a label property graph model, and this is something that is commonly stored in a graph database. So what you have to remember is that graphs are not charts. So usually people, when we are talking about graphs, people are visualizing charts. And I mean, that's fine, but it's not the same. So you just have to have in your mind that graph is a totally different kind of structure. And we are going to learn more about that structure today. So we have different kinds of graph types. We have something that is called undirected graph. So this is a graph where edges don't have an orientation. We also have directed graphs, so edges have an orientation. We have weighted graph. This is a graph where edges have assigned numerical values. And we have a multigraph, where two nodes may be connected by more than one edge. These kind of graphs can, of course, be they're mixed, like some graph can be also a directed graph and a multigraph and so on. But this is kind of a basic division of graph types. So what are we going to do with these graphs and why are they even useful? We have something called graph analytics, also called network analysis. And this is the use of a graph-based approach to analyze highly connected data. So it's actually a set of tools that helps you understand relationships between nodes and identify values or uncover insights within the data. And graph algorithms are a subset of those tools. The most common problem that are being solved with different graph algorithms are finding the shortest path, graph coloring, cycle detection, finding influential nodes, community detection, and so on. Maybe this is something you are not familiar, maybe it is, but these are certainly the most popular problems inside graph analytics that can help you solve different kind of they can pinpoint something that is specific to your data set, but you have to think about your data set more in detail to discover which problem you actually have and how are you going to solve it. So let me speak a bit more about certain graph algorithms. So in general, what is an algorithm? So it's a finite list of well-defined instructions that outline exactly how to complete some task. So graph algorithms are used to solve problems related to graph theory. They are used in different domains such as economics, aeronautics, physics, biology, and so on. And there is a vast amount of them. But we can learn something more about the most important ones. There are different group of algorithms, and maybe the most common are graph traversal, centrality, and path finding algorithms. These are probably the most used ones. So I think it makes more sense that I explain a bit about them, and you can always do a bit of research later on what's else out there. But this is kind of something that is probably needed in some basic project of yours where you want to do some kind of graph analytics. So first, a bit about graph traversal algorithms. So graph traversal is a process where you have to visit every node in a graph. You can think of a postman that has to visit all of the houses in your block. So some nodes can be visited more than once, but usually you want to revisit some nodes as infrequently as possible. There are two main graph traversal algorithms. They are called breadth first search, or short BFS, and depth first search, or DFS. So let me tell you a bit more about them. So breadth first search algorithm, as you can see on the right, starts from a single node, and the order of visited nodes is decided based on node's distance from the source node. This means that when a certain node is visited, it can be safely assumed that all nodes that are fewer relationships away from the source node have already been visited, and that results in the shortest path from the source node to the newly visited node. Depth first search, on the other hand, is an algorithm for traversing through the graph also, but it starts at the root node and explores each neighboring node as far as possible, that is, as deep as possible. That's how you can remember which one is breadth first search and which one is depth first search. So depth first search algorithms goes in the depths, while breadth first search just expands through the same level of nodes in a graph. The moment this algorithm reaches a dead end, it backtracks until it finds a new undiscovered node, and then it traverses from that node to find more undiscovered nodes. In that way, this algorithm will visit each node in the graph. Next, we have centrality algorithms. The results of this algorithm will actually give you the answer to the question, what characterizes an important node in the network. So it provides ranking, which defines these important nodes. The applications of these algorithms are usually identifying most influential users in social networks, key infrastructure nodes in urban networks, superspreaders of disease, and so on. You can find different kind of applications based on the data set you have and the meaning this important and influential node may carry. So it doesn't have to always be the best, the most influential. It can be like the worst. It depends on how do you model your data. Most popular centrality algorithms are degree centrality, closeness centrality, between centrality, cat centrality, and PageRank centrality. And I'm going to tell you a bit more about two of them. So first we have between centrality. For each node, this is the number of times a node acts as a bridge along the shortest path between two other nodes. As you can see on the photo below, like the biggest node is the most influential one, and that's because it has the highest between centrality. And as you can see, it is really standing along the most shortest path between any two nodes, and that's why it's so important. Other algorithm that we are going to talk about is called PageRank centrality. This algorithm actually came from Google, and if you represented nodes as pages and directed edges between them as links, then this PageRank algorithm outputs a probability distribution that represents the likelihood that a person randomly clicking on links will arrive at any particular page, and that's why Google uses it. To rank the search results. So this kind of makes sense. This is just one application of PageRank algorithm to measure an influence, but it can be used in many different use cases. In the end, we have path-finding algorithms. So they search a graph by starting at one node and explore adjacent nodes until the destination node is reached. And generally, we want to find the cheapest route. So it's connected to the shortest path problem that also has a goal of finding the path that best meets some criteria. So it can be shortest, cheapest, fastest, and so on between two nodes in the graph. The most common path finding algorithms are Dijkstra's algorithm and A-star algorithm. So a bit about them. So Dijkstra algorithm finds the shortest path between nodes in a weighted graph. With this algorithm, you can find the shortest path from starting node to all the other nodes in the graph. A-star algorithm is a variant of Dijkstra, and it's most often used in games. It assigns weight to each open node equal to the weight of the edge to that node plus the approximate distance between that node and the finish node. That approximate distance is found by heuristic and represents a minimum possible distance between that node and the end. So these are just two algorithms, pathfinding algorithms. There are many of them, and there are many of other graph algorithms out there. This is just like these are just the most common ones, so that you can just get a feel of what's out there. But you can always explore a bit more, and I'm going to show you later on in a code how to use these algorithms easily with some Python tools. So we talked a bit about what are graph analytics and what are graph algorithms, what's out there. But maybe you still didn't get a feel of when to use them. What are the most common graph use cases? So let's talk a bit about which companies use graph analytics in their day-to-day job. So as I mentioned, Google uses PageRank to measure the importance of web pages. Then we all know about Facebook. They use community detection algorithms to detect like which users are similar, and based on that, they can tell you they can give you more tailored ads. Also, Amazon uses collaborative filtering. We didn't talk yet about this, but it's another type of algorithm for recommendation. Pinterest uses advanced graph machine learning to give you more personalized recommendations, as well as Uber Eats. So these are actually all popular companies. There are many else out there, but it's interesting how maybe you haven't heard about graph analytics before, but you are actually watching the results of them every day. So as I mentioned, social networks are a really huge example of using graph algorithms on a graph. So this is an example of social network where you have a node that is labeled with user. We have relationships between different users of type friends with, and each user has, let's say, name as a property. So here we have a network of users that are friends with each other. And what we can do here, we can detect different kind of communities, let's say, with community detection algorithms. We can maybe do some kind of link predictions, and in that way recommend someone that you be friend with some other user. So you can do different kinds of stuff here. It depends on what is your use case, but this is an interesting example of learning more about graph databases through the social networks. Next, we have recommendation engines. So here we have nodes that are labeled with movie, user, and genre, and we have relationships of type rated and is genre. And in this kind of example, you can learn how to do different kinds of recommendations of movies based on the similarities of the users, and let's say two users are maybe similar because they rated the same movie and so on. Another good, let's say, more business example is in supply chain management. So here we have some raw suppliers that delivers something to the supplier, which delivers some kind of product that is being distributed. So here you can detect weak links and maybe then act on time and make sure that everything gets delivered. And in that way, you can do this different kinds of business risk analysis and so on. In the end, we have fraud detection. So fraud detection is a really good graph use case. So there are different kinds of fraud detections. So the most popular ones are credit card fraud detection and insurance fraud detection. This here on the image is a graph data model for the card fraud detection. We see that we have cards, we have transactions, POS devices, and so on. And what you can do here with community detection, let's say, you can determine different fraudsters that are working together, and in that way you can make sure that the next fraud doesn't happen, and so on. Next, we are going to talk about graph analytics tools. That is the most popular tools for graph analytics. So we have many developers tools in the world of graphs, and they include data modeling, machine learning, and business intelligence tools, and so on. But we are mostly interested in the graph analytics libraries and toolkits. So there are many toolkits out there, and we tried collecting them all in some kind of graph technology landscape dataset. And you can see on the right a couple of them. And actually, these are not all Python tools. So like the most popular Python tool for graph analytics is called NetworkX, and we are going to talk more about NetworkX. If you want to research a bit more about what we collected in the graph technology landscape in 2022, you can head over to our GitHub repo and find all the details there. Let's go through the basic concepts in NetworkX. So NetworkX is a Python package for the creation, manipulation, and the study of the structure, dynamics, and functions of complex networks. It offers data structures for graphs, digraphs, multigraphs, multi-digraphs, as well as standard graph algorithms. It enables you to load and store networks in many data formats, build and analyze network structure, generate types of random or classic networks, and much more. It is a great starting point for someone looking to get quick insights from their data on the fly. So what are the graph types? As mentioned, there are different kinds of graph types. They are called graph, digraph, multigraph, and multi-digraph. So you can see on the photos how they differ from each other. And regarding the naming convention, we have nodes, and relationships are called edges, and properties are called attributes. This structure is kind of similar to the label property graph that I mentioned before related to the graph databases. Now you may be wondering how to create a graph. So NetworkX graph objects can be created in one of the three ways. You can create it using the graph generators. So these are standard algorithms to create network topologies. You can create it by reading from different formats or by adding edges and nodes explicitly. So here are the couple of examples of graph generators. There are many types of graph generators inside NetworkX. You can see it all on their website. So they actually created predefined network structures, and you can continue on exploring it and learning more about graph algorithms. So you don't have to think of your own graph, but you can use predefined one and just head over to the exploring it and learning about graph analytics. Here on the photo on the right, you can see karate graph example of how it looks like you just generated with one line, and that's it. Another way of creating a graph is by reading a graph. It can be imported from many different sources and file formats that you can see here. And below you can see how you can, for example, read a CSV file and then create a graph from it. I'm going to show you later on in code examples how to use these different methods for reading graphs. Third way is by adding nodes and edges, and you can have any hashable Python object as a node except none. And as you can see below, there are different methods to add and remove nodes. This is really useful if you want to create some kind of small graph for your project, but it kind of gets a bit messy if you want to create a big graph because you have a bunch of code just for graph creation. And then if you want to create a graph of millions and millions of nodes and edges, it kind of gets really complicated. As you can see, edges can be added in a similar way. Again, any Python object can be assigned as an edge attribute, and they can be added as weighted edges or just like a simple edges and easily also removed. Yeah, as you can see on the example here, we added some nodes from a list, we added some edges, and in the end, you have the resulting graph on the right. So we learned how you can create a graph. You can create a graph, as mentioned, from different file formats, but it's kind of hard if you want to connect to many data sources and then extract the data and create a graph, because your code gets really long because of the boilerplate code, and then in the end you get the least time to actually do the graph algorithms. But regarding the graph algorithms, NetworkX really offers a wide range of graph algorithms, and that's why people like it so much. So there are community detection algorithms, Gerben-Newman, fluid communities, label propagation, different graph traversals, like we mentioned, and pathfinding, connected components, centrality measures, and so on. There are so many of them. You can see it on their websites, and they are really good. People love them because they are pretty fast. But sometimes if you have a large data set and you want to run one of these algorithms, everything that you run first has to be loaded in memory as these Python objects, and then an algorithm is being run on top of that data also in memory. So sometimes your memory can get pretty fast. It can be spent pretty fast, eaten up, and things get stuck on a large scale. So yeah, this is kind of a common issue with NetworkX, but don't worry, because there are other tools out there which actually solve these kind of issues. So yeah, I'm going to talk a bit more about these other solutions out there. But NetworkX is certainly a great choice for beginning of your project and for cool graph algorithms. In the end, we have graph drawing for the NetworkX, but as you can see it also on their website, they told that they are not primarily a graph drawing package, but they do offer a basic drawing with Matplotlib, an interface to use GraphViz. So actually a lot of Python developers know about Matplotlib, since it's like it's not that complicated tool and library to use. As you can see on the right, this is how simple graph is being drawn. I just generated some graph and draw it with a Matplotlib, but graph is kind of not that interactive. If I want to get something else on the graph, it gets a bit complicated. I have to learn all about this tool. So it's kind of not my best choice when it comes to graph visualizations. And yeah, I'm going to talk a bit more about that on the later slides, to tell you what's else out there, so that you can present your solution, your results best to the other people without creating a bunch of lines of code and learning all about Matplotlib and GraphViz. So yeah, but this is again awesome for the beginning of your project, maybe for creating some proof concept and for many other things out there. But there are certain use cases when these things get messy. And also if you want to draw a really huge graph, it's kind of hard for these libraries and NetworkX to handle all of that. So we are going to talk also about the solution to that. In the end, you probably calculated everything. You maybe visualized your graph. You have the results, and you are wondering, okay, now it's all in memory. Once the program is done, where are my results? Where is the graph that is maybe changed? I want to save it. I want to load it in some other project, in some other script. So you have the ability with NetworkX to write these graphs in different file formats, as you can see here. So the same way you can read graphs, you can also write graphs. And on the right, you can see how Peterson graph is being written in a adjacent list format. On below is just a photo image drawing of this graph. So this is again awesome. It's good to, if you want to reuse some of the graphs you created in a different project, then it's easy to just export this graph in some file format and then again import it. But just remember that each time you import this graph, it again has to be loaded inside memory, in your memory. So if you want to change something in a graph that you already created, while the algorithms are being run, you have to all over again just change the graph in the code and then run it, and it again has to be loaded in memory. And sometimes this is not good if you have lots of changing data. And nowadays, I think a lot of data is streaming, real time, changing. So it's kind of good for a small static data set. It's not that good I mean, it cannot be used with so many different data sources, real-time data sources. So that's you can get stuck with this if you have some use case where you want to explore graphs that are being dynamic and you want to make the most out of it. But let me show you all that I talked about with NetworkX. Let me show you how we can add data, how we can write graphs, how we can visualize them with a simple code snippets. So yeah, let's jump to VS Code. Okay, so finally we are on the code part. I'm going to show you what we talked about from the NetworkX basics, how to create a graph, how to fire up some graph algorithms, how to do some graph drawing, and in the end, how to export a graph that you created. Okay, so first, let me show you what we have in graph creation. We first talked about the graph generators. So here I'm going to show you how to generate a simple graph using predefined graphs from NetworkX. So you don't have to worry about the visualizations for now because this part is going to be explained later on. But first you have to concentrate on this part. So this part is actually the part where we generate a graph. So here, this is actually a network of characters in the novel of Les Miserables. And I wanted to get that graph, generate that graph, and I did it with the help of NetworkX. So I just imported NetworkX as NX, and I just called this method, and this method is going to give me this generated graph. So this graph is actually showing like a network of characters, and each edge has a weight that shows how many times they both appeared in the scene together. So here we have a simple drawing that is going to show those weights and this networks just so that we can confirm that everything is really loaded and that we really generated a graph. Okay, so I'm going to hit up play and fire up a script. And I get an image here, just a sec. So this is it. This is what Matplotlib draw. This is just a default view. This is just a simple graph with some blue nodes and with edges that have attributes of weight between them, as I mentioned. So we just see that this is now here. And if we want to do more, we can just run some algorithm, but we are going to talk a bit about that later on. So this is how you use simple graph generators. Next, we talked about data import. That is, we talked about reading graphs from different file formats. So first, I'm going to show you how to read from a JSON list. So what is this adjacent list? Let me show you here. I have an example of this adjacent list. So here we have a common example called Zakari's Karate Club network. So this is actually Karate Club social network that shows the interactions of club members, different interactions of club members, and it was used most often in community detection cases. So it was used to research and explore how different communities can be found in a network based on the interactions between the members in a social network. So this is kind of common data set that is used to showcase the strength of community detection. So here we are going to use this. This is kind of how every adjacent list looks like. And how you can import it is just with a simple method called read adjacent lists. And that's it. And I just draw it the simplest way possible without adding any options at all. As you can see, you just have to import matplotlib pyplot and that's it. So if I fire it up, I just get it. I just need to pull it here. So this is what I got. This figure is showing this data set, Karate Club. It's actually not showing anything special here. You can always like put some attributes, you can draw something more interesting. If you run community detection, you can color the nodes based on the community they belong to. But as I said, we are going to do stuff like that later on. Next, let me show you how to import a CSV file. So here I wanted to use two different methods of importing a CSV file. The CSV file that I have is just a simple file that has some source and target, and this means like I have a node of ID 1 and 2, and those two are connected with an edge. So that's kind of the meaning of this CSV file. And I imported by using this method from pandas edge list or parse edge list. So it depends on what I want to use. It has kind of different arguments, but in the end, it's very similar. You just have to decide which one to use. So if we don't want to use pandas, I just put this if else here so I can showcase. So first, we are not using pandas, so we are using parse edge list method. So if I hit it play, then this graph is being drawn here. So it's actually now currently in memory, and it's really being read from the CSV file. And if I want to try it with pandas, I just put true here. I save it, I hit play, and just a sec, sorry, I click play, and in the end, I end up with, again, the same figure. And that's it. So actually, as you saw, if you have a data set that is in CSV, you need one of these methods, and you easily can import your data set. In the end, I wanted to show you, I mean, it's not in the end, it's in the end of this reading type of data import. So you can use this read GML method. It reads GML files, and this is how they look like. So I found some data set, like a free data set online of power grids. And here, actually, this is a quite huge file. So we have like, is it directed? It's not. It has nodes and it has edges that are defined with source and targets. So this is kind of how graph is being shown. So in order to import this, I'm using readGML method. I'm giving it a path, and that's it. So I can easily do this. So let me first uncomment this part. So with this part, I'm going to draw it so that you can see how it looks like. Now, be careful because first, let's actually see how large is the actual graph by printing out the number of nodes and number of edges. So let me push play. So I'm not drawing anything. I'm just wondering the size of it. So it's almost 5,000 nodes and 6,500 edges. Okay, so that's kind of, in my terms of graphs, it's not a large graph, but if you try to visualize it, so let's now uncomment this and try visualizing it with matplotlib, you're going to see that it takes a bunch of time. I mean, at least I think it takes a bunch of time. So I'm going to run it and I'm going to wait for it. And I'm going to show you as soon as it's up. So what actually happens in the background, the graph is being loaded in memory. So as we saw, that was done pretty fast. But in the end, it all has to be drawn with matplotlib. And I guess this takes a lot of time. And each node has to be drawn, each relationship between nodes. And here we have some basic setups, such as node color. So it's black. It's nothing like, it's not anything specific, and a simple layout. So yeah, finally we got a graph, and this is how it looks like. I mean, it looks pretty cool, but it took a bunch of time to get that. But yeah, as you can see, it's kind of nice. We have these dots that are nodes, they are black, as I said, and edges that are connecting them. So it looks kind of cool. I mean, it really is cool, but we just waited a bit for it. But it's nice. Okay, and in the end, let me show you how to add nodes and edges with these methods that we mentioned before. So you can add just a node, or you can add nodes from some list of nodes. You can also, in the same way, add edges. So here, this is how I added one node. This node has some ID 1. It has a label I mean, it has different attributes. These are called label, name, and age. So label is person, name is Kevin Bacon, age is 64. So I'm not sure if you are familiar with Kevin Bacon, but he is an actor. And actually, there is a story about 6 degrees of Kevin Bacon. And it says that if you find any person in Hollywood, it's going to be connected to Kevin Bacon in a maximum of 6 degrees. Let's say this means that if you connect every person in Hollywood that acted together, you are going to, from each person in Hollywood, you're going to get to Kevin Bacon in 6 steps, in most of 6 steps. So to show you this, actually, this is a simple example where we have Ian McKellen, James McAvoy, and Michael Fassbender, and we added them too, as you can see here. We added multiple nodes, and once we added that, we also wanted to add edges. So we wanted to add the connection of who acted with who. So here we can see that Kevin acted with James. We can see that Kevin acted with Michael, Ian with James, and Ian with Michael. So we can notice that we actually don't have a connection between Ian and Kevin. So we are wondering which degree is Ian from Kevin. So let's then draw this graph. This is a simple drawing of this graph. As I said, we are going to talk a bit about that later. So let's fire this up and see what we get. So we got this graph. As you can see, all actors are here and the relationship between them. And you can see that James and Michael haven't acted together, but they are connected through Kevin and Ian. But you can also see that Kevin didn't act with Ian, but did with Michael and James. So Ian is actually, we say, Kevin of number 2, and James and Michael are Kevin of number 1. So they are just 1 step from Kevin, while Ian is 2 steps through Michael or James. So if you just said, okay, let's find a person from Hollywood, okay, let it be Ian McKellen, you can say, oh, Ian is just 2 degrees from Kevin Bacon. So it's actually like a fun story, but also a fun graphic example of how you can determine, let's say, how many Kevin Bacon degrees someone has. Okay, so we managed to create a graph, and next thing we are probably going to do with it is analyze it. So we mentioned a couple of graph algorithms, and they were divided in different categories, such as graph traversals, centrality algorithms, pathfinding algorithms, and so on. So let me show you kind of basic stuff, what you can do, some kind of graph traversals, centrality, and pathfinding algorithms, so that you can see how it's easy to use them on imported data set. So first, let's head over to the graph traversals. We talked about BFS and DFS. Let me show you that. So we are going to import a data set from a graph file. This file looks like this. So it has kind of a label called Go for start node and other nodes. So you can see that Go is connected with A, Go with B, Go with C, and so on. So with BFS, how we are actually using it. So this here was for the graph creation, and this here was for the drawing. And in the end, we got the BFS tree. So it returns an oriented tree that is constructed from a breadth first search, starting from a source. And here we see that source is a Go node. And in the end, we draw it too, because we wanted to show with red color, we are going to show how BFS tree looks on our graph. So when I click play, what I get this graph. So this is the graph of all nodes from the file, but with the red color and directions, you can see how BFS actually looks like. So the shortest path from the Go node, so this from the source node to the, let's say, node D is through A. So this was really simple example, but it's cool how you can visualize it both on this plot and see how BFS tree looks like. With DFS, it's, as you can see, the code is pretty similar, but just the result that you get is not the BFS, but rather a DFS tree. So as you can see, it's going in the depth, disoriented tree, and it's kind of different from the BFS tree. Next, so I showed you how to do simple graph traversals. Next, we can go to the centrality algorithm. That is algorithms. So here is a bunch of code, but let me just tell you what I did here. So here I'm reading a graph. Let's see what kind of graph this is. This is kind of a strange format, but actually what you see here is that we have some credit card, we have like a type of credit card, we have a person, okay. What else? We have a category, transaction. So these are some kind of transactions, let's say. And if you go to centrality algorithms, we can see that we can fire up easily different kinds of centrality algorithms and notice how different results they give. So here I use degree centrality and I just drew it. I use closeness, betweenness, cuts, and PageRank. And I wanted to show it all on one plot, and this is why I use this draw network method, and this is here. So what this method actually does, it divides the plot into 5 subplots where I can draw this between the centralities, and also it generates new colors for the new values and so on. But you are going to see this once I fire this up, how it looks like. Okay, so let me just expand this a bit. This graph is actually showing us all 5 centralities that I used and different colors based on the values of these centralities. And as you can see, it's not the same. It depends on which centrality you use, you get the different results. So it depends on what actually you want to get from the data set and how your data set is modeled, because like the results can be totally different and you can use them in a totally different form. So make sure to like study the theory first of each algorithm in order to know which algorithm to use. Okay, and in the end, for graph algorithms here, I have Dijkstra. So actually, this is the shortest path algorithm that uses Dijkstra's implementation. And I'm going to show you how it calculates the shortest path. So first we have some graph. Let me show you this graph. So it's like we have a node that is labeled with go, we have a node A, and we have a weight or length of a relationship between them, edge, and in this example it's 7. So for each node that is connected to another node, we have some number that is length or weight, however you like to call it. So here what I'm doing, I'm saying, okay, this is going to be called weight, and I'm going to import it from this. I'm going to read this edge list from the file. This is for the drawing again, so this is like simple for the let's draw this layout and so on. And here I'm doing the shortest path. And in the end, I want to tell you which are the shortest path from the source node called go to all the other nodes. So let's fire it up. So we are going to push play. We are going to run this script. Great, and we got an image, but let me just first open up this graph. Great, and we have this image, so we can check what's happening here. So on the right, we can see that the shortest path from the go, that is the source node, to the node A is actually just from go to A. That makes sense. It's of weight 7. And if we, for example, went through the node B, we would have, as you can see on the left, 6 for go to B, and from B to A we have 2, so that equals 8 in weight. So it makes sense to go through A. Also, you can just try all the other options, but I assure you this is the shortest path. And also you can see more complicated shortest path as like from go to G. We can see that it's go to B to F to G, and below you can see that this path weights 14. And if we decided to go through C and then G, we would have on the left, you can see 8 plus 7, and that equals 15, and that's more than 14. So you can play with it, you can check whether it's all correct, but on the right side you can have this nice, you can print this out nicely so that you can easily understand what the algorithm calculated. Next, I want to show you how to do simple drawings of your graphs, how you can change some things up, what you can do, but feel free to explore more because there are many other options with Matplotlib. You can also explore GraphViz. I'm going to show you here how Matplotlib works. Okay, so first thing I'm going to show you is how we have different kinds of draw methods. It may be confusing at first, but I'm going to show you how they both work so that you can differentiate one from another. So here I want to draw a complete bipartite graph, and I just used draw method in the first attempt of drawing it, and in the other one I use draw NetworkX. So these both methods are using Matplotlib. The difference is that this is kind of a basic drawing. And as you can see here in the docs, you can use Draw NetworkX for more full feature drawing. So it allows different kinds of options that you don't have in a simple draw method. And it's kind of useful when you want to do something more complicated, something more colorful, and so on. So let me fire this up and show you what you actually get. So this is the drawing with the first draw method. So it's kind of okay. It has this default NetworkX blue color, edges between nodes, and that's actually it. Okay, so let's see the other one. What happened in the other one is that we, by default, got this labels inside the nodes. So we have these numbers that are the IDs of the graph nodes. We have edges, and you can notice some kind of rectangle around this. And this is actually called axis. So here we have axis shown, and I'm going to show you how to turn that off later on. Okay, so this is kind of the biggest difference between these two methods, and you can play with it with different examples, and I'm going to also use both of them, so you're going to see where to use one and where to use another. Another important thing regarding the visualizations drawing in NetworkX with Matplotlib is layouts. So you can position your graph in different kinds of layouts depending on how is your graph connected. So you can use one layout and it can look perfectly, but you can use another layout and it can look terrible. So you just need to try it out. You need to figure out like what type your graph is so that it's best to use some layout other than other layout. So first, we created this graph, we generated this graph with NetworkX, so we don't have to deal with the graph imports. And okay, sorry, this is it. This is the docs on this generated graph, and we are just simply drawing it. So we want to see what happens if we just press play. If we press play, we get this. So this looks really nice. So what's good about this is that actually it seems that this basic default layout works good for this graph. And the basic default layout is actually called spring layout. So it positions nodes using this force-directed algorithm. And this algorithm actually says where the nodes of the graph should stand based on the edges that they are connected with. So this, as you saw, looks really nice. And now I'm going to show you, this was the graph. And now I'm going to show you how this graph looks in another layout. So there are a bunch of layouts out there. You can see it all on NetworkX documentation site. But I'm going to show you here a couple of basic ones that I use most often. So let me comment this and I'll do this. So this here is going to be a shell layout. It positions nodes in concentric circles. So I expect something circular, and let's see what do I get. So this is the graph, so I expected good. It looks like some kind of ellipse. Okay, it can be a circle. Cool. So this is some kind of net, but it's still, our graph still looks nice. I mean, it still is representable. Okay, let's try the third one. The third one is called spiral layout. So I guess we know what to expect. And I also forgot to mention that, as you can see, this is how you are actually using this layout. So you are giving the argument to the method draw called pos. This pos is actually a position. And this position, as you can see in the documentation, can be a dictionary with nodes as keys and positions as values. And as we mentioned, the Spring layout is the default one. So you can give it a layout or this dictionary. I'm going to show how to give dictionary in next example. But this here is easy to use because NetworkX just provides done layout, so you don't have to worry about that. You just pick a layout that suits you best. Okay, let's see the spiral layout. Oh, this is kind of cool. It actually looks like a shell, and it's not a shell layout. It's really nice. I like it. So this is the third way of drawing this. You can try it out in many different ways here. So good luck. Okay. Let's now I'm going to show you the dictionary part. So again, you can use, as I said, positions, but let's first fire this up and then I'm going to explain what happens. So I'm going to press play and show you the graph. Okay, so let's explore this drawing a bit. As you can see on the left, I have positions, and this is a dictionary whose keys are the IDs of the nodes and values are the positions. So how do you even consider these positions? How do you look at this? How do you see this on the graph? So as you can see here, we have some figure and we get the current axis. So this represents this variable that represents axis, so x, y axis. Okay, so here we set the axis off so that our drawing looks a bit nicer. But let's comment this so that we can actually see the axis, and maybe that helps us a bit with the explanation of what happened. Okay, let's fire this up now. Okay, this is what we get. So these are the axes. So it's again kind of strange, but if we see the values that we have here, we can kind of notice that this must be node 0. This is 1, 2, 3, 4, and 5. Why? Because if you look that the x-axis goes here horizontally, and the y-axis goes here vertically, then this is actually like 0 because it's -1, 1. This is 1 because it's 0, 1. This is 1, 1, and so on. So how to check that? Let's turn the labels on. So how did we even say, okay, let this node size be this, color this, labels, yes, no. So we added options to the draw NetworkX method. So as I mentioned, that draw NetworkX method allows us to do more stuff. And this stuff is kind of this. So I can add node size, I can add the color, I said just red, or you can add in hexadecimal code. I said use this graph, put it at certain positions. So this is the pos argument, and we have different set of other arguments. So this is the options, and we have with labels. So we see that here we turned off the labels. Let's put this to true. I guess the default is true, but let's do it like this and fire it up and see if we were right regarding the labels, regarding the nodes positions. Okay, so I guess we were right because we can see actually 0, 1, 2, 3, 4, 5. So we correctly said where are the axes, and now you can draw it however you like because you know the positions. Let's try to do it. Actually, I think it's quite easy. If we just do like this, then what do we even expect? We expect this first node on the left to go like totally up, and the kind of graph won't be that nice, but at least you know how to use positions. Okay, let's see if I got it right. Let me show you the screen. Okay, so I got it right. I had this in my mind. Not sure if you had it. You can play with it more and see whether you got these positions, axis, y-axis, vertically. Did you got it right? Do you have it inside your mind? But this is kind of what you get if you change this a bit. Okay, in the end, I'm going to show you how you can style your graph. So here we have an example of a data set. I'm going to show you how it looks like. So here we have some person, again, transactions, accounts, and so on. So we have some kind of graph data model for some transactions, credit card transactions, possibly for fraud detection. Let's see how we can style that graph. So we are using the NumPy library, and this library gives us this method called linspace. What this allows us is to generate colors for each node so that each node has different color. It's great for drawing graph schemas because like you want each node that has different label to have different color. We are giving it a circular layout. I mean, you can give whichever layout you want because this is going to be a quite simple graph schema. You are going to see how it's connected, so it's not that important. I'm going to use draw method and just give it some simpler stuff. And if you don't want to use directed graph, you can just add arrows false, so that's also possible. Then what else you can do? So since we use draw method, we also want to add labels like node labels, edge labels, and you can do that with the draw NetworkX labels and draw NetworkX edge labels method. So you can do all of that. You just have to get some node attributes that you want to have as labels. And here we have label for the nodes, type for the edges, and you just use this method to draw them. And in the end, you need to show that with matplotlib. And let's fire this up, and I'm going to show you what we got. So as you can see, it's really nice. It's nothing complicated. We have a store that is of category. We have a store that has post device, transaction, add some post device. Credit card has a transaction. A person owns credit card, and a person has account on social media. So this is the data set that I was talking about, and it's kind of nice to see this as a graph schema, so you can always recognize what data you have inside, what data do you have prepared, and you can see how it looks like actually. So in the end, we talked about how you can write graphs in different file formats. So I'm going to show you that. Here we have a script where we are writing a generated Peterson graph. You can see here what is a Peterson graph. So it has 10 nodes, 15 edges, and so on. And I'm going to write it into 3 different file formats. So a JSON list, GML, and GraphML. And yeah, the output is going to be here, and I'm drawing it just to show you how this graph looks like. Okay, so as you can see, it's easy. I just use this method and it's done. So if you here, instead of generated graph, you maybe created some of your own graph, changed it, added some new properties, that is attributes, and so on, maybe generated some new results, then you can finish up with doing this and saving your actual graph and reading it from another project. So let's start this up. Okay, so once it's done, I got this figure. This is the Peterson graph. Okay. So you can see that it's actually being generated. And in the data folder, I can see that we have this. Okay, this is a JSON list, so we have this. This is GML. We saw this kind of files when we were reading graphs, and this is GraphML. So we have everything generated here, and you saw how it's simply to write graphs with NetworkX. Hopefully you enjoyed the demo part, and I encourage you to continue learning more about NetworkX. There are a bunch of other methods which you can use, so just head over to the NetworkX website, documentation, and head over to Memgraph's resources to learn more about NetworkX. Now let's summarize everything that we learned about NetworkX. So we learned that it's a great tool for Python developers, which allows you to quickly fire up a large set of graph algorithms on your dataset. You saw how it's easy. So if you just want to play around with it, you can simply generate predefined graphs. You can read from and write to different file formats, and as you saw, you can create simple visualizations with Matplotlib and GraphViz. But the data in NetworkX is static, and every time there is a change in the data source or analysis code, you notice that you need to reload the dataset. Also, due to the Python implementation, many NetworkX graph algorithms become too slow with millions of nodes and relationships. Another thing is that NetworkX is, like I already mentioned, not primarily a visualization tool, so the solutions it offers are often too slow and not interactive. Besides that, you have to learn how to use those tools. Another thing is that writing endless lines of code to create production-ready applications takes away the time from the work you actually want to be doing, and that is analyzing the data. But don't worry, there are other tools out there. I mean, NetworkX is awesome, but I'm going to present you another tool that solves these couple of issues that I mentioned, and that tool is Memgraph. So Memgraph is an open source platform for graph computation and streaming data that is powered by in-memory graph database. You may be wondering, why would I even need a graph database? We mentioned definition of graph database. We mentioned label property graph that is being stored in a graph database. But why would you need a graph database? So a graph database usually stores the data as a label property graph. And since the data is stored inside the database, it doesn't have to be loaded every time you want to run a new algorithm or when you want to change the data. So that's kind of different concept than in NetworkX. You can collaborate with other people on the same data set with changes over time, and in that way gain the most accurate insights. There are different solutions out there. So we have on-disk solutions or in-memory graph databases. In-memory graph databases offer faster analytics, but are often not persistent. That is, they don't ensure data durability. On the other hand, on-disk solutions are common permanent storage solutions, but when it comes to the fast analytics, they lose the battle. Okay, so what does Memgraph have that maybe offers the best solution for the issues that were mentioned with NetworkX? So with Memgraph, you can load the data once, even from multiple and real-time data sources, and focus on the querying and analysis and not the tedious and manual importing and data managing. So you avoid all the boilerplate code. Due to the C++ implementation of Memgraph and highly optimized storage memory usage, Memgraph outperforms Python-implemented NetworkX on both small and large scales. We also mentioned issues with visualizations in NetworkX, but after querying the dataset directly with Memgraph, you can shape the results so they reflect the insights you discovered in the best possible way. You can do that by using Memgraph Lab. You can interact with the graph, export the data, and present it to others. And another thing, no coding is necessary to import the data. You can run algorithms, visualize results, all out of the box. So you can use a wide range of NetworkX algorithms as well as Memgraph's graph library image. Yes, you heard it well. You can use NetworkX algorithms inside Memgraph. Another thing worth mentioning from the Memgraph ecosystem is GQL Alchemy. Since you are Python developers, you may be familiar with the SQL Alchemy for relational databases. This is similar, just for graph databases. It's a fully open source Python library. It's an object graph mapper. That is, it is a link between graph database objects and Python objects. So it includes OGM capabilities, query builder, graph schema validation, on-disk storage, importers for different types of objects, and NetworkX integration. What NetworkX integration does, it actually offers you transformations so that you can transform your existing NetworkX graph into Memgraph graph. And how are Memgraph graphs stored? So, as I already mentioned, they are labeled property graphs, as you can see on the image on the left. So here we have a user that retweeted some other user, and each user has a property username. So in GQL Alchemy, Python client, Memgraph's Python client, you can do this like on the photo on the right. So you just have to import Memgraph node and relationship classes. You connect to Memgraph by creating an instance of Memgraph class. You create classes to define schema. So we have class user as a node, so it inherits from the node class. It has property username of type string. It has class retweeted that inherits from the relationship class. It doesn't have any properties, so we just pause. And we are creating here two users with names John and Jane Doe. We are saving it to Memgraph by using method save. And we are creating a relationship between those two nodes by using their internal IDs and saving it to Memgraph. So it's that simple to create a schema and to create a simple graph inside Memgraph with Python. But enough talk, we can now do the demo. I'm going to show you how to create a simple database inside Memgraph using Jupyter Notebook, that is using Python code. And we are going to explore the graph we have with the help of Memgraph Lab. In this demo, I'm going to show you how to connect to Memgraph with its Python client called GQLAlchemy on a simple example of movies dataset. First, you have to start Memgraph with Docker. It's the easiest way to run Memgraph. And we are going to run Memgraph platform image because it contains everything we need. It has Memgraph database. It has Memgraph lab, that is a visual user interface. It has MG console command line interface and Mage, graph algorithms and modules library. So let's first fire this up. I'm going to copy this command. If you are following up with me, you can do it too. And next, I'm going to open up terminal and paste this command. So once I hit enter, this container is going to be run. And as you can see, I'm connected to Memgraph, and this thing that you see here is MG console. So what I can do here, I can type queries. So Memgraph, you can communicate with it with Cypher query language. It's the most widely used language, and I kindly recommend you to try to learn it. It's not that hard. You're going to see it in this demo. And if you learn Cypher, you are going to easily use most of the graph databases, and I think it makes more sense to learn that graph query language. Okay, so if I do here, I'm going to show you that our connection works by creating a simple query. So let's say match n, and then return count n. What this does, it actually searches for all nodes in the database. And as you remember, this is a graph database, so it has nodes and relationships inside. That is, it doesn't have anything now inside. So we expect this count of nodes to be 0. Okay, we click enter and we can see that the result is 0. Okay, so this is kind of maybe if you work with relational databases, you're used to this kind of command line tools. And this looks okay, but it's not that pretty. And I actually don't use it a lot. I most often use Memgraph lab. So since you fired up Memgraph platform image, you get Memgraph lab out of the box. So you can go here, you can go localhost 3000, and you end up with this screen. So this screen is actually quick connect. It detects that the Memgraph is running on your system. If Memgraph is not running on your system, the message, you won't be able to connect to Memgraph lab because it doesn't recognize any connection to Memgraph. So if I just click connect now, this was some of my latest queries, so it gets remembered. This here is the query execution part. So this is where I type queries such as the one I did before. So we can do that again too. So match and return count n and run query, and this is the result I get. I get that the count is 1. So this here now is not that representable and doesn't make that much difference, but I'm going to show you how if you have a graph as a result, things get much prettier. Okay, so I'm going to introduce you to everything that lab has to offer later on through the demo, but let's return to the Jupyter Notebook so that I can show you how to connect with Memgraph. So we did the first part. We run Memgraph, so everything is there. As you can also see in the Memgraph lab, we have 0 nodes and 0 relationships inside the database, so it's empty for now. And we want to put a movies data set inside. So let's first explore how the data sets look like. So here we have pandas library. So it's a simple Python library that's going to allow us to read just a small part of the CSV files we have. So the first file is called movies CSV. Here we are going to look at the head of this file. And as you can see, each movie has a movie ID, it has title, and it has genres. So this is kind of not the perfect way of having this data since genres are split with this pipe, but we are going to handle this with the Cypher query language on import. Next, we have ratings. So each user that has a unique ID rated some of the movies. It gave some rating and at a certain time, so we have a timestamp. Okay, so the next thing we have to do is to create a graph model for the data we have. So this is kind of a tricky part when it comes to complicated databases, complicated data, but in this case, it's not that hard. So you just have to think about what are the queries which you are going to perform later on and what is going to be the most efficient way of doing that. So if I think of this data set, I'm thinking that I would like to know, let's say, how many movies are of genre adventure, or I would like to know how many users rated some movie, and so on. So maybe what makes most sense to me is to have a node that is labeled with movie, to have a node that is labeled with, so I'm going to show you here that is labeled with genre, and to have a node that is labeled with user. So as you can see here, each movie is going to have its ID and title, each user is going to have its ID, and each genre is going to have its name. So these nodes are going to have relationships between them of type rated and of genre. And as you can see here, rated is actually going to have properties too, called rating and timestamp. So here, if you refer to the tables above, you can see that we actually have all this data here. So we modeled it right. We just have to look after how we are going to actually import it with GQL Alchemy. So first, I'm mentioning GQL Alchemy, but we still haven't connected with Memgraph through our Python code, so let's do that. In order to do that, you will have to use GQL Alchemy. You will have to first install it. So currently here I'm using version 1.3.2. So make sure to use or the latest version, or if you're having troubles, just use the version that is here. So first, you have to import Memgraph class here from GQL Alchemy. So this Memgraph object actually is the object that represents a connection to Memgraph instance. So you create an instance of that class, and you are telling it it's going to be run, and it is run on localhost port 7687, as we noted in the docker run command. And first, let's drop a database. I mean, we haven't put anything inside, but it's a good thing to do that once you start running your database or your project. So as you can remember, I did some basic query in MG console and mgraph lab, match and return count 10, that gives us like a number of nodes inside the database. You can see that I added this part as number of nodes. This is an alias that is going to be like the name of the header of the table that is returned as results. So this is how I can do it with GQL Alchemy. I just run execute and fetch command that is going to give us the results back of this query. Inside I put a cipher query and I print out the results. And as we thought it is going to be, we have a number of nodes that is equal to 0. So what's the next thing we have to do? So in order to import our data, we can just import it and not think about anything. If we don't have anything in our application that needs to follow a certain schema, that's totally fine. But probably if you are creating your whole application, you would want your data to have a certain schema, so that if anything goes wrong with the data, if there is some kind of property missing, you would want this to be noticed and that you can change it accordingly. So you don't want to have a messy data inside the database. So the best way to assure that is by defining a graph schema. So GQL Alchemy is an object graph mapper. It's similar to SQL Alchemy if you use it for relational databases. So this allows you to create these classes for certain types of relationships and certain types of nodes. And here, since we have a movie, user, and genre nodes, we are creating those three classes. So we are creating them. They are inheriting from the node class, and we are defining their properties and the types of their properties. And if there is some certain constraint to this certain property, we need to tell that too. So for example, here, we have on the movie ID, we index it. This means that the import is going to be much faster because we index the ID property since we are matching on the movie's ID. Unique means, okay, there is only one movie with a certain ID. So there shouldn't be two movies with the same ID. Exists means that each movie must be defined with its ID. So there shouldn't be any movie in the database without the ID property. And we need to give it a database because these kind of things like indexes and constraints are going to be created as soon as you create these classes, not when you create an instance of a class. The same goes for the class user. So we again have ID that has a bit more constraints, but we also added a constraint on the name. Maybe, I mean, this is just an example here, but maybe you want to say, okay, I want this name to be unique. I just added this here because I wanted to show you how this works, but I added it also as an optional property. Next we have genre. It's nothing special. It just has its name. And we have two classes that represent relationships. Here we added a type property. That's because in the database it's like common to write relationship types with the uppercase. And I like to keep it that way. And this is also a good thing because if you want it to be named differently in the database, but still work with your classes in a totally different way in a class name, you can do that too. So we defined this everything. Let me spin this up. Okay. So next, what we want to do, we want to create, I'm going to show you how to create and return nodes and relationships. So first, how to create a simple, let's say, user and a movie and the relationship between those two. So to create a user, you create an instance of a user class, and let's say my name, Katarina, and I'm giving myself some ID, let's say 1, and I'm creating a movie with ID 1 and title Lothar, so Lord of the Rings. Okay, so to save that inside the database, I could go here like save, but okay, let's do it here. .save memgraph, and I'm printing it so that you can see what's actually in the database. So first, do you trust me? Is this in the database? Let's head over to the Memgraph lab. You can see that we have 2 nodes. Let's see which nodes. So if I do match n, this here is telling us that it is a node, and this is the variable name. So match n, return n, goes, okay, give me all nodes in the database and return all nodes. This is a good thing to do if you have 2 nodes. It's not a good thing to do if you have, let's say, tens of millions of nodes. Okay, I'm running this, and what I get is this nice visualization. So I have a Katarina, I have a user node, and I have a movie node. You may notice that this here is a label. It's not the name of the movie. That's because Katarina actually has name property and movie has title property. And here we have something that is called graph style editor. And this editor allows us to change the look of the graph below. And as you can see here, if the node has property name, we put its label to be name. So we can do the same thing for the title so that each movie also has this. So I'm just copy pasting this and adding title. It can be done in a more elegant way, but this language is kind of similar to CSS, but we call it GSS. Okay, so great. I just applied this style, and once I apply this style, as you can see, I have my both of names like title and name here. So I can see that I created 2 nodes. That's fine, but I still don't have any relationship in the database. So let's head over to do that. But first, I'm going to show you why our constraints were important. So if you can remember, I defined a constraint to the username to be unique. And now let's try to create with a cipher query language another user whose name is Katarina. So I expect an exception. I expect that the user with the name Katarina is already in the database and that I cannot create this user. So what I'm doing, this is a create cipher query. It creates a node because it has this, and it creates a node of label user, and with properties. So this is key value pairs in some kind of a dictionary. So property is name and value is Katarina. Okay, so let's try to create this. Okay, so we run into an exception. So user with the name Katarina is already in the database. So you cannot create another user Katarina. So to prove that, you can see that this create query did not go well because we don't have 3 nodes in the database, we have 2 nodes. Next, let's create this relationship between this. Let's say I wanted to rate Lord of the Rings. I want to give it a 5 and I say, okay, rate it now. So the timestamp must be now. So I'm going to use time library from Python. I'm going to create a new instance of rated relationship. And I'm going to give it start node ID and end node ID. So let me just explain this a bit. As you can see here, we have an underscore and what this actually means. So if I return back to the printout of the nodes that we created before, you can notice that they have some ID, but then again in the properties you have ID. So these IDs are the IDs that I gave them as a unique property, which I defined in my schema. But these IDs are called internal IDs. So this is something that Memgraph generates for each of the objects. And you can see that I can have ID 1 for user and ID 1 for movie, since it's unique for each node of label user or of label movie, but Memgraph sees it as node objects. So these node objects must have different internal IDs, and these IDs go from 0 and so on. So this is 0, 1, and so on if I created new nodes. So this is something that we need in order to create a relationship, because with the object graph mapper, because if you want to do it with Cypher, you can do it in different kinds of ways. You can do matching through properties, names, and so on. But here we want to give this rated relationship arguments with internal node IDs so that it knows exactly which nodes to connect. So we have start node ID. So that's why we saved user node when we created it, because through underscore ID we get its internal ID. Same way we go with the end ID. So we want the direction of the relationship to be from the user to the movie, because the relationship type is rated, and rating is I give it 5 out of 5. And timestamp is current time. And okay, let's start this up. So in return, we got this rated. This is its internal ID. So it's 0 and it's fine because it's not a node, it's a relationship. It has start node ID, end node ID, nodes that it consists of. It has its type and it has its properties. Now let's see in Memgraph Lab what actually happened. So as you can see, we have now one relationship, and you may be wondering how to see that in Memgraph Lab. So what we need to do is we need to create a certain pattern to match everything in the database that we want. Let's say we want to match all the nodes and relationships between them. We have to do this. We have to create another bracket. This bracket represents a relationship, and we can put a type inside, but not for now. It's not necessary. We declare a direction of this relationship. We declare another node. So we have a node related to another node, connected with another node, and we return all 3 of those. So it's kind of intuitive. And once we do that, as you can see, we have Katarina who rated Lothar. So if we click on this relationship, we get more information. We have that it's of type rated, we have its rating, we have timestamp. On each of these nodes, you have again its properties. So everything is, you can explore everything. You can, currently we cannot expand because there is nothing else in the database. We can collapse. If we collapse, then I think Katarina is the only that is going to left. So if we expand, we have again this. There is a bunch of things which you can do here, but currently this is a too simple example to show you that. I'm going to show you that on a larger scale. Let's now try to import a bigger data set. Let's head over back to the Jupyter Notebook and import data from the CSV files. So first, let's clean up the database. So we just run drop database. If we turn back to Memgraph Lab, we can see that it has 0 nodes and 0 relationships. Okay, so what we have to do to actually copy these files. So we have to copy them inside a Docker container where our Memgraph is running in order for it to see it from the Cypher query that we need to run. Okay, so let me open up a new terminal window, and let me show you how to find out where is everything located. So first, I'm going to locate myself inside the folder of this course. So I have it saved here. If you copy the repository of this course, you can also locate yourself inside the data folder of Memgraph directory. So it's here, Memgraph Academy. Okay, and if something changes, you are going to have all the resources, so don't worry. And here and here. Okay, so here we have movies and ratings CSV. So next I need to find out in which Docker container Memgraph is running. So I need to find out Docker container ID. In order to do so, I'm running docker ps command. With this command, I get every details about the running containers. So I have a container ID. I'm going to copy this container ID and I'm going to copy the file. So as you can see in the Jupyter notebook, I gave you all the instructions on how to do that. So we have docker cp for docker copy command. We want to copy movies.csv. It's located in the current folder, so no issues here. We paste the container ID. And then we say it's going to be named movies CSV also in the Docker container. So this is actually like a mapping to Docker container. Okay, that's it. And we do the same for the ratings CSV file. Okay, and it's going to be called ratings CSV file. Okay, I messed something up because I didn't go with ratings, but rating. That's fine. Okay, that's it. So now I copy it into Docker container. If you are not sure whether it's there and you want to know how to explore Docker container, you can do it like this. So Docker execute in interactive mode, container ID and bash. And now I'm inside the Docker container. And I just check what's inside. And as you can see, this is all files related to and folders related to Memgraph application. But here we also have in the root movies and ratings. You can also place it in some kind of folder, but it was not necessary for this example. So the next thing I can do is load the CSV files, and I'm going to use Cypher Query. To do that, I'm going to show you later on that you can also use something called a query builder if you are not willing to learn that much Cypher. But this is kind of simplest way to load. This is the fastest way to load data inside Memgraph using the load CSV clause. Okay, so let's go. First, we need to load movie CSV. And if you remember, we have a movie ID and we have a title of a movie. And also each movie had a genre, but this genre was kind of one data that was like each genre was split with a pipe. So we have to tell that to Cypher Query language somehow. So we first load CSV from movie CSV file and we give this with header as rows. So this load CSV clause can hold with header or with no header. But here we have header because the CSV file holds the first line that says, okay, this is movie ID, this is title, this is genre. So we have this and we want our load CSV clause to ignore this so that it doesn't have to read the first line. And then we say, okay, load it as row. This means that each iteration of this algorithm of this load CSV clause is actually going to read everything row by row. So for each row, create something. So what we want to create, for each row, we want to create a new movie. And this movie is going to have its title, is going to have its ID. So in this way, we are creating a node. And this node is labeled with movie and it has properties. And these properties are ID and title. And we want each movie to have this ID as integer. And we want this movie to have a title. And this is by default a string. So this here, as you can see, we are reading it from the current row. So as you are, like you are going through the columns of your rows in a table. And now we need to take these two. So we have still row, we have RM like a movie. So with those two, we want to split that genres cell with pipe character. So we are doing this here. And each of these is going to be named genre. So this is now kind of a list, and we need to use unwind clause that is going to say, okay, split this list, unwind this list, and for each of these genre, create another node. And this node is of label genre. But what we are actually also creating here is for the movie that we created before, we are creating a relationship between that movie and all of the genres that it belongs to. And these genres have their names, and the relationship is of type of genre. So it's maybe too much for now, but if you go back and then listen to me repeat this all over again, I think it's not that difficult to understand. You can search all of these clauses in Memgraph documentation and learn more about them. But let's now run this and see whether it loaded well. Okay, so let's head over to the Memgraph lab, and we can see that currently there is around 30,000 nodes and 22,000 relationships. That's great. So we created movie and genre nodes and relationships between those two. So if I now do this, and let's limit the results to 100, then I can see that it's a totally different stuff. Let's go here. Okay, so we have a movie Balto, and it's of genre children, animation, and adventure. Cool. So we know that what we have in the database. We can also head over to the graph schema tab and generate graph schema and see that currently this is the only thing which we created in the database. And if you compare this with the graph data model that we created, that we draw, we can see that we still have this part kind of missing. Okay, so the next thing we need to do is finally load the users and connect them to the movie they rated, as you also saw on the image above. So we now are loading from the ratings.csv, where we have this data. We are finding the movie that is in the certain row of this CSV file. We are finding it in the database, and we are then creating a user, but we are using merge, not create clause, because we don't want to create new user for each row. And next we are creating a relationship between the user and existing movie of type rated. And each of these relationships have properties called rating and timestamp. So if we execute this, you are going to see in Memgraph Lab that we have higher number of relationship and nodes. And if we now do this, you can see that situation is kind of different. We can see here that we have some movies, we have some users. Now we have different types of relationships, so you can write a better query. I'm going to show you how. So let's say we just want relationships of type rated. And I will put a bit higher limit. Okay. So let's do this. Okay. So we have a movie. This movie is Toy Story. And as we can see, it's rated by a bunch of users. So this is some user with the ID 100. And they rated the movie with rating 4 at a certain time. Great. Let's see the relationships. What is the other type? I think it's of genre. Okay. And now we can see, again, a movie of some certain genre and so on. You can also do both. We just have to put a higher limit. You can play with the data set as you like, but you can also head over to the graph schema, generate it, and see that now we finally acquired what we wanted to do. Great. So the next thing we have to do, what I'm going to show you, is a bit how you can query the data set. So what you can get, what interesting data you can get. And next we are going to talk a bit about graph analytics on this data set. So, let me first show you some basic queries. I mean, we got a lot of them already, but here I wanted to show you how you can work with Query Builder instead of the Cypher queries. So first, I'm going to show you how Cypher query looks like so that you can easily see how to work with Query Builder. First, we do execute and fetch command in order to execute a certain query. So here I'm trying to find a movie, and I'm returning this whole node, but I'm ordering the results by the movie title in ascending order and limiting the results with 10. So, when I do this and I start this up, I can see that I have some set of movies and I have them ordered by their title. So this is kind of a very useful Cypher clause and also limit. So this is a simple matching and that's it. Okay, so you may be wondering, like we have here, you can see that this is kind of serial as back, and that's a great thing. So once you get the results back from the Cypher query, it automatically recognizes that this is an instance of a movie class. So that's great, because if you haven't created a class inside your code, it's going to give you a little warning and say, okay, you didn't define this subclass of node. So is this something you don't want to have in your database, or did you maybe forget? So this can be useful, and also this can be useful because this means that you can use the properties like a class properties. So you don't have to go you don't have to search with Cypher query the exact title, but you can return the whole movie and then with dot title get the title of a certain movie. In this example, 500 Days of Summer. And as you can see, I printed out the type and it is really a class instance of class movie. Okay, so let me show you now how to do this with Query Builder. So I need to import a couple of things from GQL Alchemy in order to do this. And next, I'm just doing all of this like above, but I'm doing it with the clean Python code. So I'm doing a match, as you can see also here, and I'm doing match node, and I'm returning the results. I'm ordering them by something, limiting the results, and in the end, I have to tell to GQL Alchemy to execute this code. So in the node, I can declare different set of properties, and in this example, I just need label, and each node can have multiple labels, and that's why this is labels here. I also need a variable because I'm going to order by this property of this variable. So I'm ordering it by the title, and the order is ascending. I imported this enumeration class, and I'm limiting with the 10 results. So I expect the same result as above. So this is how you can do it too with your Python code. It's maybe more, maybe you are more used to this stuff. Okay, let's now head over to some other example queries. Some simple one, we already did this. So, this is what we did above a few times, but this is how you can do it with, Query Builder. So, this is something that is called Cypher function, and there are many of them. You can see it in our documentation, and, we are returning this results, same as above. We are just matching node and returning and executing. So this is nothing, complicated. And we have, as we can see, we have 610 users in our database. So what if we want to find out how many users rated a certain movie? Let's say Home Alone. So we are trying to find a node that is connected to a movie node with a relationship of type rated, and that movie has title Home Alone. So like I said it now, that's how you create a query. So you go match node to node. So match user node to movie node, and with relationship of type rated, where the title of a movie is equal to Home Alone, and give me back the number of these users. So with the count function, and execute. And that's it. So 116 users rated the movie Home Alone. Okay, how we are going to find the genres of a certain movie. So as you remember, we have a movie, and this movie is connected to the genre nodes with the relationship of type of genre. So we are trying to find the movie. with a certain title that is connected to bunch of genres, and return those names of those genres. So match node to node, match movie node to the genre node, where the title of the movie is Blue Lagoon, and return this genre. So Blue Lagoon is adventure, drama, and romance. So who likes it, go for it. Okay, next let's see how to list 10 movies of comedy and action genres and sort them by title. So here you are going to see how you can use order by, where, and similar limit and everything else. So a match node movie, we are matching movie to a certain genre. This genre is comedy and action. So first we are matching it with, let's say, action, and then we are doing then we want to find out which of these movies is also a comedy movie, and we are doing this here. And in the end, we are returning the titles of these movies, and we are ordering them by title. And you just have to be careful, like whether it's ascending or descending, and that's it. Okay, I don't know okay, that's it. Then we can find out the average rating of the movie Star Wars Episode 4: A New Hope. So this is interesting because, again, we are using a different cipher function called average. So this is really cool for some ratings, for some prices, whatever you need in your data set. So we are trying to find all of the users that are connected to the Star Wars Episode 4 movie. And we want to return an average rating that is on a property of the rated relationship, and that's it. And with the help of this, we can find out that Star Wars is pretty good rated, so it's 4.23. Okay, so this was all just a simple querying. I'm going to show you now how to do a bit more. We talked a lot about graph use cases, and one of the most popular graph use case is a recommendation engine, and it can be a movie recommendation, it can be a product recommendation, or anything similar to that. And products are really interesting use case of graph databases because these connections make it easier and faster to do the recommendations in the graph database rather than with relational database. So here I'm going to show you how to do it with a couple of lines of cipher query. This is just the simplest recommendation. Nothing is extra custom, is just using collaborative filtering, and we are going to implement this query with the memory-based approach that uses user rating data to compute the similarity between users or items. So now we are doing this just by executing this cipher query. As you can see, we use execute and fetch method. And this is the query with which we get the results. So for the users with the ID 608, this is our target user, we have these movies as its recommendations. And you can see here, this is kind of a prediction rating. So the user would like mostly like this movie, but kind of wouldn't like these movies that much, let's say like that. So, okay. Now, let me explain you this query in parts so you can get like what's happening. So it has two parts. First, we are trying to find all the similar users. And in the next part, we are showing and predicting the score for some movie. So we are actually giving the recommendation. So how we are looking for similar users. So we have our target user and it's with ID 608. And we want to find all of the movies that this user watched with some other user. So what means watched? I mean, user rated a movie, so user must have watched the movie. That's how we are looking at it. So as you can see, user rated some movie, and this same movie was rated by some other user. So this is the only of the other users. But that's not enough. So we can say, okay, users are similar if they watch the same movie, but we want to find the users who watched the same movie and also gave similar ratings to those movies, because that's what makes them similar. So we did that with this formula here. that calculates the similarity. So it's being calculated as the average distance between the target user, so user with the ID 608, and some other user rating on the same set of movies. So this similar user count limit, as you can see, it has to be higher than 2. That's used for filtering users that have at least 2 movies in common with the target user. So we don't care if 2 users watched one movie together and rated it similarly. It doesn't give us like a great similarity. We want them to to have watched at least 2 movies, 2 same movies. And then we have the similar user set. And that will give us like a top 10 similar users. If some user doesn't have top 10 similar users, it's going to give us less, but no more than 10. Because we think 10 is good enough to give a good recommendation for all of the movies to the target user. Once we've done that, we have the other part of the query. And this part of the query is actually calculating the prediction rating for all the movies in the database. We have a user that rated a movie and we want this user to be in a similar user set. So we are just checking the ones that are similar. And we are finding the average rating. With this average rating, you actually get some kind of a prediction rating. And if we order it in descending order, then we get like the best average rating on top. And that's how you know that the first result is actually the best recommendation. As you saw above, like the first one is 5.0, while the last one is like 2.0. So it makes sense, like the first one is the best recommendation because that's the prediction rating. You can play with this query. You can set up different parameters, similar user count, similar user set. You can change this limits, maybe get different results. And you can also change the similarity function. So here we had this simple similarity function. You can also use something like Euclidean distance. This would look like this. So go ahead and play with it. As you can see, this is nothing hard, but if you want to implement your own recommendation system with Python, you can also do that. And I'm going to show you later on how to do it directly from Memgraph Lab. Next we have something related to graph analytics, like the algorithm that we already talked about. And maybe the most popular algorithm is PageRank. So the great thing about Memgraph is that you have a bunch of already prepared graph algorithms. So I'm going to show you like the easiest way to see those algorithms. Here we have something that is called query modules. So these query modules are actually each query module contain a set of procedures, and these procedures are now currently already implemented. So these are all the procedures that are already implemented. But you can also create your own custom modules. So this module can be written in Python, C, C++, or Rust. But in Memgraph Lab, we give you the possibility to write a query module which is written in Python. So this is great for all of you Python developers. But as you can see here, we have, let's search for PageRank. So we have this algorithm here. You can head over to the documentation, you can head over to the source code and check it out. And here you can see the methods, the procedures that are implemented inside this query module. And here we have a get procedure. This procedure actually calculates the PageRank values for like PageRank centrality algorithm for each of the nodes that you want it to be calculated. And I'm going to show you now how we are going to do it on this data set. So you can either fire up this query module on a subgraph. So you can do some kind of matching and then give an argument to the PageRank get method of this subgraph, and in that way just do the calculations on one part of the graph. But here, since this is not that large of a data set, I'm going to calculate the PageRank on everything, and then I'm going to filter it out. I'm also doing this so that I can show you how to filter out, but later on I can also show you how to do it on a subgraph. So in order to do this, we are actually just calling this method with the call procedure. This is kind of basic way of calling any procedure. So we are yielding everything that the procedure returns, and then we get node and rank. I think this was written here. So actually that's it. This is what our page rank get procedure returns. And then I'm going to filter the results by the label. So I just want to get the movies. I want to find out which are the most important movies in the data set. So let's say most influential. That would be probably the most rated movies. So I'm going to return the node, so the movie title actually, and its rank, and order it in descending order so that I get the best ones first, and limit the results by 50 and just print out everything. So as you can see, I obtained the results, and the first movie is The Shawshank Redemption. I think that pretty much makes sense because I think it was, or is it still the best rated movie on IMDb, not sure. But these are all kind of good movies, so I think it makes sense, but it doesn't have to always make sense. It's best if you can somehow customize the things you want to do or model the data best. So next thing I'm going to show you is how you can create a custom procedures on a data set in Python so that you can get most out of the Memgraph lab features. So first, let me show you how to create, in general, query module. So I'm located in the Memgraph lab that I have running at localhost 3000 from Memgraph platform. You can also download Memgraph lab as a desktop application and use it on your computer. But this is the simplest way for now. I don't have to download anything. I don't have to install anything. I just spin it up. So if I head over to the query module section, I have, as I already said, listed all of the procedures that are there. But if I want to create something new, I just click new module. And let's say I call it my little example and create it. So what I have here now is some sample code. It's all written here. You can write different kind of read procedures or write procedures or functions. And this is here how you should do it. You have some basic information about that. On the right, you can see which procedures are being detected. So you can notice if you didn't implement something right, you're going to see everything that happened wrong in the logs. And on the right, your functions won't be recognized as Memgraph procedures. Okay, so here we have some basic procedures. Let's save and close this. So they are written in Python. We have hello procedure, we have hello function, and I want to try out this procedure. Not sure how to use it, but here I can see it's quite simple. So my little example is the name of my query module. Hello procedure is the name of the procedure. This procedure has an argument. This argument is just some kind of any argument, and it's giving back the message, input argument, and vertex count. Okay, so I'm going to copy this. I'm going to query execution, paste this, and here I'm just going to type in graph analytics course. Okay, and let's run the query. And hello Memgraph, graph analytics course, and count 0. So yeah, this is just a simple example. It's nothing smart, but it's useful to see how you can easily create your own procedure in Python through the through Memgraph Lab. Okay, now let's do something more interesting. Let's first load some of the example data sets so I can show you. So let me just find here something. So we have a bunch of data sets here which you can play with, but I'm going to load this music genre social network. Let me just click load data set, confirm, wait for it. It has around 2000 nodes and 5000 edges, and I can run simple query just to see what happens. So as I can see, I'm finding all the nodes here and finding all the number of pop genre inside the data set, but let's see the graph schema so that we figure out what's happening. So we have users that are friends with another users, so that's kind of pretty straightforward. And each user has an ID and genres. Okay, so each user has a set of list of genres that he or she always likes and is friends with. This relationship doesn't have any special properties. So what we can do now, we can just, like we did now, we can just query it like this, and it's fine. But if we want to do something else, we can do it with the query module. So I prepared here, I created a new module called the Deezer example. And inside these modules, I implemented two procedures. So if I head over to the edit code, I can see how they look like. So these procedures are called genre count and intop and percentage. So first one is just counting the all of these genres and how many users have these genres. And the other one is counting which genres are in the top and percentage of each user. So which genres are the most likable by the most users. Okay, so let's save and close, and let's try it out. So first one is not that, let's say it's not that smart. So if we go here, we can see how to use it. We can copy it, go to query execution. And let's say we want to count, let's say rock, since we already had pop. And this is it. So it's counting how many rock genres there are in the dataset. So nothing smart. You can do it simply with Cypher query. But if we decide to run this other example, it's a bit more interesting. So we are counting just a sec. Okay, this is pasted. So we are counting the genres which are in top and percentage. Here, as you can see, we gave it an argument 3. This tells us what percentage each genre appears in the top 3 places. Okay. So this is the percentage. So Dirty South is in the top 3 places in 96% of this data set that is in the users. We suppose that each user has added genres, it added genres one by one, and if they added first genres, then this first genre is most important to them. That's how we ended up with this analytics. So this is just to prove that you can write this kind of procedure. I'm going to return to the procedure so that you can see how it's being written. So you just have to give it this read procedure here because this tells us that this is a read procedure. This can also be a write procedure. We need to give it a context because the context is telling us what's inside the database, and that in that way you can reach the whole graph and its vertices, and you can do different kinds of calculation inside your Python code. Hopefully you liked the demo I showed you. I, of course, didn't have enough time to show you all of Memgraph's features, but I wanted to show you one more thing. So this is related to Memgraph and NetworkX integration. I'm going to show you how to use the benefits of both. So if you really like your NetworkX project, your NetworkX script that you already created, but still want to get a data persistency, still want to get an easy visualizations and easily deploy your application, then maybe you can use NetworkX code with Memgraph. So what actually means that Memgraph is integrated with NetworkX? This means that you can use a large set of NetworkX algorithms inside Memgraph, such as all shortest paths, clustering, DFS tree, between centrality, and so on. You can also utilize NetworkX library to create custom procedures inside query modules. I showed you how to create a query module, and this means that you can just import NetworkX library and work with it inside the procedure like you're used to. That's how actually Graph Analyzer and Weakly Connected Components algorithms from the Mage library were created. Another thing that Memgraph team created for seamless integration is a set of transformations inside GQL Alchemy. These transformations allow you to transform NetworkX graph object into Memgraph from your Python code. After the data is stored inside Memgraph, you can explore it with Memgraph Lab or run Memgraph graph algorithms. So, as I said, you can avoid all the boilerplate code because you can do it all with Memgraph. Memgraph lets you do all of the annoying data imports from multiple static or real-time data sources. So you can connect to a stream of data, create certain query modules which you use to explore this streaming data. You can run dynamic graph algorithms which allow you to obtain the results faster from the newly created data. And you can also use your existing NetworkX code by writing it as a Python query module inside Memgraph Lab. You can visualize and analyze the data quickly with Memgraph Lab, and I'm going to show you how you can play with graph, how you can style it to obtain the best possible results. And that's not it, because you can also deploy your application easily since you have to only maintain one service, and that is Memgraph. So, enough talking. I'm going to head over to the demo. I'm going to open up Memgraph Lab again and show you how you can use your NetworkX code with Memgraph. So we are back to our Jupyter notebook, and I'm going to show you how to import NetworkX graph into Memgraph with GQL Alchemy transformations. And I'm going to show you how to use best of the both worlds, best of the NetworkX and Memgraph, and how to visualize your graphs easily. So what's actually inside GQL Alchemy? I mentioned transformations. So GQL Alchemy holds in transformations that allow the NetworkX graph to be transformed into the Memgraph graph. And these transformations take the NetworkX graph object and translate it to the appropriate Cypher queries. Then the Cypher queries can be executed so that the graph is created inside Memgraph. As you can see here, we imported this transformation and we connected to Memgraph. We dropped the database just to make it all clean. We created a NetworkX graph. We added nodes to it and edges with these methods. And we just ran for query in NX to Cypher transformation. We transform this graph into queries and we execute these queries. So once I do that, I can head over to the Memgraph Lab. I can see that there are 3 nodes and 2 relationships. And if I run this query, I can see that this graph is actually stored inside Memgraph. So what's actually inside? We have NX to Cypher and NX graph to Memgraph parallel procedures. And we use the first one. So by default, the node does not have a label and the edge is of type 2. That's why when we had this graph, we only have one node that is labeled with first, and the other ones don't have a label, and we have one edge that is of type edge type, and the other ones don't have a type. If we see it here, we see that this is the exact thing that happened. The number with which the node is defined in NetworkX node translates to property ID in the Memgraph node. So if additional properties are defined in the dictionary of a node, then they will be translated to node properties in Memgraph. We just have to be careful because if we give properties that have keywords, labels, and name and type, they are reserved for the label of a graph and type of an edge. So you just have to be careful with that if you like to add some new properties. So here we can see Memgraph Lab that actually the number is really translated to the ID property. So if we want to add new properties, then we just add them as a new dictionary, and we can see here that we added a new property of name to the node of ID2, and we added a new property date to the edge of type edge type. So if we run this and we fire up here, we can see that a thing changed a bit. So this one has name, and this edge type actually has a property called date. Okay, so that's kind of basic stuff if you want to translate your existing graph into Memgraph. But usually you're going to use Memgraph as your data import tool, since it's much easier for Memgraph to handle different data sources that are either static or real-time, and you don't have to worry about that, and you don't have to have a bunch of boilerplate code just for importing the data set. So let me now show you how you can analyze and style the graph and what's else out there in Memgraph regarding NetworkX integration. So first, let's create a new graph, and this graph is the Karate Club graph that we talked about in the first part of the course. So I'm using NetworkX graph generator to create this graph, and I'm just translating this into Cypher queries for Memgraph and creating a graph. So if I head over to the Memgraph lab, I can see that we have 34 nodes, 78 relationships. I run this and I can see that everything is inside. So what actually is also here? We are aware of the importance of graph algorithms, and we decided to write the wrapper object for Memgraph's graph with better usage of NetworkX algorithms. So to make things more convenient, we implemented procedures that call NetworkX functions with Memgraph graphs, so that you have out-of-the-box access to the graph algorithms. The NetworkX algorithms are stored in the NX query module, and there you can find many implemented procedures. So to show you, when you are in Memgraph lab, head over to the query modules. And if you type in NXAlg, you're going to see that you have 78 procedures here. You can see which procedure those are. If there is something missing, you can always open a PR and do it, or you can use custom query module. Or you can maybe check out whether Memgraph has those procedures outside the NetworkX query module. So besides that, we implemented some of our own query modules, some of our own procedures that utilize NetworkX library. So two of them are Graph Analyzer and Weakly Connected Components. So if you go here to query modules and I go to Weakly Connected Components, I can see that there is one procedure called get. And if I head over to the Graph Analyzer, I see there are 3 procedures: analyze, subgraph, and help. So I can show you actually how this procedure works. So if I call this one, I'm going to see all about my graph. So this is we collected a bunch of simple procedures from the NetworkX library, put it into one query module, and then you get all of these results with just one command. And this is something that is pretty useful when you start working with your graph, so that you know how it looks like and what kind of algorithms you can run on it. We also work really hard on our own graph algorithms library called Mage, which outperforms NetworkX algorithms, and it also has dynamic implementations as well as static ones. So to show you, these are all our own procedures from the Mage library, and if you can type in PageRank, we also have PageRank as well as NetworkX, but this has different implementation. It is implemented in C++, and therefore it's much faster. And we also have an online version that is the dynamic version, which allows you to obtain results fast as soon as the new data is coming into the database. And this makes sense to use if you have a graph use case where time is of essence, such as credit card fraud detection or similar to that. So next I'm going to show you how to analyze this graph and how to style it, and I'm going to use a combination of NetworkX and Memgraph algorithms to show you how you can use the best of the both worlds. So I have prepared a couple of queries. What I'm going to do here, I'm going to run a PageRank algorithm and community detection algorithm, and I'm going to set rank and community properties to each node. And once I have that, I can easily style the graph based on those values. So I prepared a query collection here called Karate Club, and in this query collection I can run pre-prepared queries, and here I prepared, as you can see, community detection here and PageRank by NetworkX. So first let's run PageRank by NetworkX and set this rank. So this is done. I have no results since I just set the values. And I want to run community detection by Memgraph and set the community ID. So once this is done, I will return all the graph. So let me go to the latest queries. I have this, I will run this. Okay, so this graph doesn't tell us anything now. So actually each of these nodes holds a rank and community values which we set before, but this visualization is nothing helpful for now. But what I'm going to do, I'm going to style it a bit. So let's return to the Jupyter notebook. And here I have a style file. And I prepared this file so that each node has different size proportional to the rank values. And also with this query, I determined how many distinct communities are out there. So if I run this, I have 4 communities that are detected. So I didn't want to worry about, since I know that there is only 4 communities, I just did this like this. It can be done in a more elegant way, but this is totally fine for our use case. And I have 4 simple colors, and that's it. So if I head over to the Memgraph lab, if I again run the query to show the whole graph, go to graph style editor, select all, and paste my code. So this is like the whole code that I had, and I apply it. I can also save it for later use, of course. I get this graph. So this graph is now telling us a bit bigger story. So I can see here that this node must be an important node. This is some kind of member of community club. It belongs to the community number 2. It has this huge rank. As you can see, this node is not that large, so this rank is much smaller. But you can also see these colors. So as I said, this node belongs to the community 2, but now I know that also this node belongs to the community 2. I can obviously see 4 communities here, and I can easily explore, drag this graph. Memgraph also has a bunch of pre-prepared data sets, so you can play with them. And one of them is Karate Club Friendship Network. So if you load the data set, you're going to get, again, same 34 nodes and 78 edges that you can play with. And I just wanted to show you how you can utilize the NetworkX library inside a custom query module. So what I did, I created a communities query module, and I can show you the code. So it's a simple query module, but it's showing how you can import your NetworkX code inside your project with Memgraph. So you can just import NetworkX library. It's all here. You can import NetworkX algorithms and use them. So if there is no similar algorithm implemented inside Memgraph library or inside NX query module in Memgraph, you can then do it here. So here I decided to use Gerben-Newman community algorithm, and I did it like this. So I created a read procedure, and I just created a NetworkX graph from the context, so from the current graph inside the database. And this one is directed graph, so I created an object called Memgraph dgraph. From that, I created a NetworkX dgraph, and then I just ran Gerben-Newman algorithm, and I returned the list of the communities. That is, I'm going to get for each community, I'm going to get a list of the members that are belonging to that community. So if I go to my query collections, I prepared the query for this. So if I close this, I can see that it looks something like that. But what I have here is this query, and I'm going to run it. So it calls my procedure called detect. It yields all the communities, and as I can see here, I have 2 communities, one of which has 15 items and one of which has 19 items. So all of the 34 nodes are inside, and if I open up this list, I can see which members of the Karate Club are inside this community, and if I open this one, I can see which ones are here. So that was an easy way of how to use NetworkX library, your usual Python code inside Memgraph, and just run it with Cypher, just like a simple procedure. So it's nothing complicated, and that way you can Stay safe with your own code, with your own NetworkX project. You can share it with others easily because they can also just spin up Memgraph as a Docker image and play with it. Also, if you decide, if you have a project that needs to be production-ready application, you need to deploy it, you need to maintain it, and it's much easier to maintain just one product that is Memgraph that makes sure that all of your data is imported correctly and that you can collect data from different data sources, whether static or the real-time ones. It's quite easier to manage that kind of project. And also, as you saw with Memgraph Lab, you get a quick visualizations with its visualization tool called Orb. So you have nothing to worry about and you can easily explore the data and of course present it to others. You also saw that you can save your favorite queries inside the query collections. You can visualize your graph schema here, and you can play with the sample data sets. I didn't show you a bunch of other features that Memgraph has, but there are other courses and other materials out there with which you can learn more about that. So that's it. Thank you for joining the Graph Analytics course, and hopefully you got to learn a bunch of new things about graphs, graph databases, graph analytics, graph algorithms, NetworkX, Memgraph, and hopefully you learn a bunch more about other tools out there. If you get stuck with anything or have any questions, feel free to join our Discord server. There you'll get to ask anything you want to know about graph analytics, Memgraph, Python, and so on. Also, if you want to check all the other useful resources we have for the NetworkX and Python developers, head over to our Memgraph for NetworkX developers page. Also, don't forget to sign up for all the other Memgraph's courses and webinars where you get to learn a bunch of new stuff about the graph technology in general and figure out what are the graph use cases and so on. That's it. Hopefully you had a great time and we'll see each other on the next Memgraph course.